Here, since everybody's over here. Waves! What's a wave?
Repetitive motion.
It's really
Oscillating.
yes, oscillating motion. I like that. Okay, a wave is a disturbance in a medium that transports energy from one place to another, but does not transport the medium itself. Okay, a wave is a disturbance in a medium. Medium is being a substance or something through which it can move. Okay, wave is a disturbance in a medium, like a wall, perhaps. What did I say? Disturbance in a medium that transports energy from one place to another. Any luck?
I'm just going to give her my schedule so she can sign up.
From one place to another, but it doesn't transport the medium itself. Okay? It is kind of magical. Now, like for instance, let's say that I want to get your attention. Daniel's in the back of the room, he's not paying attention, so I have a couple ways to get his attention. Number one is through transfer of energy by physically transferring something to him, the particle, the object that has energy in it. So like I can take this, I can throw it to the back of the room.
Go ahead.
Wait.
Greasy fingers.
All right. I didn't need the marker. All right, so I can throw something back there. The object has energy, clunks him upside the head, and Mr. Broom wants my attention. All right. Or I can transfer energy back to Daniel without actually moving anything back there. With a sound wave. Okay? Or a light wave. Right?
Or I can just look.
Or a wave. Okay. We have a couple of wave detectors on our body. One is our ears, which detect sound waves. One is our eyes that detect light waves. Okay? Our nose, on the other hand, does not detect information through a wave.
Mr. Lays.
That's particle transmission. I mean, if you smell something like coffee,
Because it moves up.
yeah, you literally have to have some of those coffee particles. Yeah, next time you smell a skunk, it's because some of the particles of the skunk odor have drifted into your nose. Okay? Yeah. Oh. Actually, a Greek philosopher, I don't remember which one it is, the one that came up with the idea of an atom. He came up with that idea because he smelled bread baking, and he's like, how do I smell this bread? And he reasoned that it's because little bitty particles of the bread, somehow or another, were coming from it and entering his nose. Which is a pretty slick little deduction. Okay?
So I can technically sniff up a piece of Christian.
Yeah.
Okay.
He's inside of you.
Yikes. All right, let's move on because it's getting a little scary. Okay, now wave transport is different, okay? Wave transport is a way to transmit energy from one place to another without transporting any material, okay? Just the energy transfer. All right, so give me a list of waves.
Sound. Light. Concussive barrages. Okay.
That's it?
Sure. Shockwave.
Oh, I thought that was in the lake.
How about like in musical instruments?
Sound. Air.
Yeah, but the musical
Vibrations.
instrument themselves, it's a different, they make different parts of them vibrate in the form of a wave. Like guitar strings or in a piano, right? The strings vibrate. Right? A drum, when you hit a drum, the surface of the drum vibrates in the form of a wave. Okay.
It's just the food itself. It's a little
And-
over.
Yeah, okay, like a flute. Like a flute.
That's not.
It is a flute.
That's
a kazoo. Hi.
I like that.
You should. Okay, flute.
You can actually play something with
How
it.
long did you practice that?
Weeks. Weeks.
I just be able to play on the recording.
All right, yes. Okay, in here, what's vibrating in here to make the sound is not like a string or, yeah, it's an air column that's vibrating. All right? So, all right, there are lots of different waves. The thing is this, whatever type of wave it is, they all have common properties. Okay, and we're going to talk about those common properties, all right? So here we go. And all of them transport information without, well, energy, which also transports information, without transporting the medium themselves, okay? Like for instance, when I speak, if I talk and talk and talk and talk and talk and talk, it's been a really long lecture. Okay, shh, shut up you. All right, if the medium, which is air, transported along with my waves, what would happen?
It'd be very windy.
Yes, first of all, you'd have
Smell
a
that.
breeze.
Yeah.
No, it'd be minty fresh.
I recommend
All right?
extreme.
You'd have a breeze as I spoke. And as I talk, the information goes out to you. All right? And the medium goes with it.
You'd have no air there.
Yeah. Okay, he's going to pass out again. All right? Because I would talk and talk and talk, and the air would leave me, right? Okay. So the deal is it transports this energy and information without transporting the medium itself. Now the medium does vibrate and oscillate, but it returns back to its normal position. Okay? All right, let's break down waves into the categories. There's a couple ways you can break down waves. Number one, you can break down the wave into its type of oscillation.
Mechanical.
Okay? There are three major types of oscillation. Okay, number one is a transverse oscillation, or longitudinal oscillation, or what we call a surface oscillation. Really a surface oscillation. I'll talk about what that means in just a minute. There's others than these. Okay? There's Rayleigh waves as well. There are other types of waves, okay? But the two that we're going to be the most interested in are going to be these two. We talk about surface waves because we see those all the time. Okay, transverse waves mean that if the wave is traveling this way with velocity, if the energy is traveling to the right, the wave itself, the medium, will oscillate up and down. So the wave will vibrate the medium up and down as it transports this way. So it'll be perpendicular to the way it's going. Those waves look like this. This wave is traveling to the right, but it's oscillating up and down. Okay? Okay, a longitudinal wave, on the other hand, is a wave that if it's traveling to the right, it oscillates parallel to that direction. Okay, there's the vibration.
Blah, 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 blah.
Can they see that? Yeah. No, they can't. All right? These are much, much harder to draw. Okay? You ready? They look kind of like this. Well, here's one way to draw.
Oh,
Then
wow.
separated. Wow.
That's so hard.
Lines.
All right, and this would be like if you had like a slinky, and the wave was traveling down the slinky. Okay? So it'd be crunched up here, stretched out here, crunched up, stretched out, crunched up, stretched out.
You should have brought a slinky.
Okay, now these, I do. I'll show you in a minute. Okay, these types of waves are always occur in gases and liquids. And the reason why is because for a transverse wave to work, the material has to be tied together. Okay?
So it's like it stays together?
Yeah,
Although
so-
when it actually moves apart, it would come together.
Yes. So what happens is these have to be tied together. And so as my elbow goes up, my forearm goes up with it, and then it'll drag my hand up, which drags the other hand up, and so forth and so on. So a transverse wave looks like this, all right? Because they're connected. Now, if my hands are not connected, then I cannot get a transverse wave to go from here to here. Does that make sense? Because they're no longer connected. So in a gas, the molecules are not connected, right? So you cannot get a transverse wave in a gas. In a liquid, liquids are similar. The liquids slide past each other, so you can't really get a transverse wave in a liquid either.
Don't water waves.
Now, water waves, when you're at the surface of the water,
Surface tension.
because of surface tension, underneath the surface of the water, you have only these types of waves. The kind where the molecule comes up, smashes the next one. It's like a car collision. Same thing in gases. So any kind of fluids, they're always going to be longitudinal. Now there is an exception of near the surface of water, you have surface tension. So you have this kind of motion, okay, this kind of wave, and this kind of wave at the same time. And what you get is this rolling motion, okay? And what happens is, as the wave transports this way, it rotates around like that. That's the vibration. But that's only at the surface, near the surface of the water. Okay? And by the way, I know that if it's rotating this way, it's going to move to the right. You all know this. Because if you see a wave like this, which way is it going?
To the left.
That
To
way.
the left. Oh, wait, to the right.
It's a nice surfing wave. It would be really bad for surfing if the wave transported this way, because you would just flop over the top of it, right?
And die.
It wouldn't push you forward. No, you'd just fall over.
Off on impact.
Okay, these types of waves, surface waves look like this. They look just like these waves, except if you were to put a dot, like a little boat or something, on this wave, this little boat here, all right, on this wave, this boat would go up and down, up and down. That's all it would do. But if you put a boat, a little boat on this wave, the boat will actually do this. It'll oscillate around in a circle. Okay? Next time you go to a water park, like Hurricane Harbor or something, get out in the big wave pool. Okay? And you can feel it out there. Get out on a floaty. And when you're out on a floaty, or just float there, you don't just do this. Right?
No.
You do. You're getting flopped around, right? As the wave goes by. Right? Okay. If you don't believe me, go home, get out your little rubber ducky, get in the tub, make waves, and the little rubber ducky doesn't do this. It goes bloop, 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 as it flops around. Okay? All right. Now let's talk terminology of these waves. You ready? Terminology is over here, crest, trough, crest and trough. Okay? Crest to crest, what do you call that?
Wavelength.
That's a wavelength that has the symbol lambda.
That's not a lambda.
That's a lambda. Oh, that's a lambda. That's a lambda. That's a lambda. They're all lambda.
I like the fourth one.
I like that. That's the one I drew.
Looks like a seven with another leg.
Seven with leg.
Yeah.
All right. Crest to crest. Trough to trough. Okay, what if I start here? From here to here? Is that?
That's half.
Why only half? I'm at the same spot.
No, you're not.
I'm at the same height.
But that doesn't.
You're right, you're not going the same direction.
But I'm not going the same direction. This one's on the way down, this one's on the way up. So I got to be in the same spot, going the same direction. So that's a lambda. Okay?
That's a line.
That's a wavelength. Now, crest, trough, wavelength. Okay, we need to know frequency. What's frequency?
One over time.
The amount of wavelengths it has to do as a
Number of waves
second.
per second, or it's the same thing as 1 over the time period.
That's it.
Okay, so what's time period? It's 1 over the frequency, but time period is also number of seconds to complete, or per wave, right? Number of seconds per wave. Right, so if it takes 10 seconds to create one wave, then the frequency is 1/10, right?
Yeah.
10 seconds to produce a wave, frequency would be 1/10, right? They're inverses of each other.
Okay.
Got it? Okay, frequency, time period, crest, trough, wavelength. All right. Over here, this type of wave, a longitudinal wave. This spot right here is called a compression. Yes, that's a compression. The spread out spot is called a rarefaction. Okay? It's rarefied. There's less there. A rarefaction. Okay, how do I measure wavelength here in this way?
Compression to compression.
Compression to compression. And it's probably the easiest way. You could also measure it rarefaction to rarefaction. But it's usually easier to measure it from compression to compression. Okay? That's your wavelength. All right. Surface wave has the exact same terminology as a transverse wave because it looks the same from the side. All right? Now, since longitudinal waves are really hard to draw, in your books a lot of times they'll do it as a fade-in, fade-out tone. So like it'll be light, dark, light, dark, light, dark, kind of like a barcode, but they'd fade it in and out. Okay?
The dark is the compressed.
The dark generally is the compression. Okay? When we speak, that's what the air does. The air crunches together and spreads apart as our vocal cords vibrate. All right? Since these are very hard to draw, even though they're not longitudinal waves and they don't look that way, we will generally draw sound waves like this. If you've ever looked at any kind of sound recognition software, anything like that, where you speak into the microphone and it shows your sound wave pattern, it doesn't show you this, what it really looks like. What they show you is, a wave like this. Because it's easier to draw these than it is to draw and visualize what's going on with these. Okay? Now, let's take a look at these real quick, and we're also going to talk about some other things about them. So, let's do this up front. Here we go. Transverse wave.
Lucy's was weak.
Come on, Lucy.
Look, it's never
Okay,
going
why does the wave, first of all, notice what happens when the wave gets to Lucy.
It bounces back, but on the other side.
It bounces back, but on the other side. Okay, now that's because when the wave reaches a new medium, Lucy, okay? When the wave reaches a new medium, which is Lucy in this case, the energy tries to transmit into Lucy. Okay, Lucy is not nearly as flimsy as this material. All right? Lucy's more dense.
Ooh, you're fat.
I'm sorry. She's stronger.
Yeah.
She's more massive.
Ooh.
Excuse me.
She's dense and massive. Okay?
I mean, she had more volume.
All right. And so what happens is this thing tries to shake Lucy's arm. When it tries to shake Lucy's arm, it cannot shake Lucy's arm very much, and so the rate at which the energy transfers into Lucy is different than the rate at which it transfers through the slinky. So the energy can't go straight into Lucy, so some of it reflects. The part that reflects is a little bit weaker because some of it actually did go into Lucy. But the part that reflects is flipped over because this is a wimpy material. It's lighter. And it's trying to shake a heavier, more rigid material. Lucy's arm, made of bone and muscle.
Muscle and bone.
She's Richard.
There you go.
Do it again.
Here, step back behind the camera. Go on.
Job.
Go on.
Good job.
Go on. Back. There you go. All right. So when it tries to shake Lucy's arm, it flips over. Now, if Lucy was made of a lightweight, wimpy material, then the reflection would come back on the same side. Okay? All right. Also, notice that no matter what I do for this wave, it travels down and back at the same speed, right? So I do this or this. They're all traveling the same speed. Here, I can show it to you because I can make a small one and a big one.
I had a seizure.
Small one, big one. And notice the big one doesn't catch the small one, right? They're going the same speed the whole time. So no matter what I do, the medium determines the speed of the wave. The only way to change the speed of the wave is to change the medium. So like if we made the medium tighter, the wave would travel at a different speed.
Oh, wow.
Okay? So now it's, oops, so go ahead, Lucy.
I just want to make sure.
She wants it to go faster. All right, so notice it goes substantially faster when I change the medium. But if the medium stays the same, the speed stays the same. So like in air is mostly the same all the time, right? So when you talk, everybody's sound waves travel the same speed, right? Whether you're singing a high note, low note, whatever. Think how bad a band concert would be if you had the cheap seats and all the waves traveled different speed because they were different frequencies.
Cheap seats.
Well, they really would be the cheap seats because it would sound horrible. It'd be out of time, right? The only seats that you would be any good would be the ones right up front, right? But in the back, even though you're really far away, it's all still in time, right? Okay. So that is a that's a transverse wave. Crest. This is called a pulse, by the way, and these are called traveling waves. All right? Now you want a longitudinal wave?
Yeah. What's going on?
All right? That's a longitudinal wave. Longitudinal wave. All right? So that's a longitudinal wave. Okay? All right, now. Lucy, I want you, here, let's make it slower so everybody can see it. Okay, I want you to make a wave that way, and I'm going to make a wave this way. All right? And I want everybody to watch what happens. Ready? Set, go.
Go right, Lucy.
Okay, Lucy, make a wave.
Move your hand right.
No, just one. Just make a pulse. Sorry. Make a pulse. All right, make a bigger pulse. All right, now Lucy's going to make a pulse. I'm going to make a pulse. All right? I want what happens when they meet. Ready, set, go.
Oh, Lucy was. Oh, Mr. Bruce was stronger.
Okay, ready,
This was
set,
dead
go.
Who wins? Who wins? Ooh, where's the
Okay,
ball?
what happens when they meet?
They bounce off, but they go both in the same direction.
They add.
They subtract to switch, don't they? They just become.
That's what they add.
Okay, I've heard they add, they subtract, they switch, and they bounce off.
None?
In this case, it's destructive interference. They
combine.
When they meet, you notice that the wave changes shape, right?
Yeah.
It's the addition of both of them together. Now, if they're on opposite sides, they'll subtract.
No, one's just in
But if they're on the same side, they'll add up. Okay? So, let's see if we can do that. You're going to make your wave this way. I'll make my wave that way as well. Ready, set, go. You see the wave get bigger when they met? Try it again. Ready, set, go. And it's hard to see because it goes so fast, right?
Slow mo.
But if I could make a wave this way, exactly the same as Lucy's wave that way, when they met, they would show no motion at all. But does that mean the wave goes away?
No.
Just
Okay,
at that point.
so they meet, but then what do? Do they bounce off or pass through each other?
Pass through.
Well, I'll prove it to you that they pass through, all right? Lucy, make one wave, and I'm going to make two waves, and we'll see which ways they go. Okay, ready, set, go. See how my little waves went through the other waves? Think about that. What if the waves would bounce off each other? I'm talking. You don't want to hear me anymore. What do? You just talk. And you would hear your waves bounce back to you, and I would hear my waves bounce back to me, and I'd go, stop it, I'm trying to have class. Yeah, and you couldn't hear me, right? So my waves go to you, your waves go back to me. They pass through each other. Now, this is substantially different than particle motion. Objects cannot do this. You're an object. If you run down the hallway and you run into somebody else, you can't pass through them. If you were a wave, you could, right? If you were a wave, you could. All right, so crest, trough, medium determines the speed, pulse, traveling waves. Waves, when they meet, they pass through each other. When they hit a boundary or a new medium, there's going to be some reflection and some transmission, depending on what the medium... Oh, okay. All right. Now, new medium. Do you expect the same speed of the wave?
No.
Wow.
Wait, do it again. I was watching. Oh my god. Whoa. Ah.
Confused.
Yeah, my head hurts.
All right. Now, notice new medium, new speed. All the other rules are the same. Okay? When waves meet, they pass through each other. They reflect off. Because David's more dense than this medium. Notice that. If I make a wave that way, it bounces off the other side, right? All right, now, we're going to see if we can get what's called resonance. Okay? All right, now I want you to start shaking it back and forth, and I'm going to shake it back and forth. There we go. We found the first. Now this is actually the second harmonic. Okay, what's happening now is I'm making a wave. David's making a wave, and the waves are passing through each other back and forth, but it looks like the wave is standing still, just flipping back and forth, right?
It's about 0.
What really is happening is energy's going that way, energy's going this way, and look what happens at the very center. They're canceling each other out, right? Almost. We're getting pretty close. This is called a standing wave. You get this when you have what's called resonance. When you're at a natural frequency of the object. Okay, this is one of the natural frequencies. Okay, let's go really slow and create the first one. Okay, the first one looks like this. Now you got the same. There you go. There's our first harmonic. Okay, now let's go faster and get to the second. There's our second harmonic. All right, faster? Wait a minute, let's start from rest, because otherwise it's hard to stop. Okay, you ready? Faster. We had it. There it is.
Oh my god!
Ow, my fingers hurt. Ow. Ow. All right.
Oh, we're like, what's going on?
That was, I think we actually got to the fourth harmonic, because there were 4 of the little loops, right? Okay, that's the fourth harmonic. Okay, that behavior right there, getting to a natural frequency where you get amplified motion, is what we take advantage of in musical instruments. Okay, that's how we play notes. All right. Now, this
So now it's Nia's turn.
That's right. Okay. Okay. First, okay, make a wave. Okay, wait a minute. No. Make a pulse. Just go like this. Go. All right. Do it again, faster. Like this.
It sounded awesome.
Sounds like...
See?
Yeah, for Nia!
Here you go, Nia. Now, if I happen to slip out of my hand or anything, Nia, don't take it personal. Ow, that hurt.
Let go of me then.
Nia's in trouble. All right, hold it right there. Hand on the ground. Hand on the ground. All right, ready? Okay, see how Nia is a denser material, but notice now, because this material is more like Nia than the Slinky was like Lucy, right? This is a more similar material to Nia's arm, right? Look at Nia's arm.
It
tries to shake.
the same way.
Do you notice it shakes Nia's arm?
Because she's weak.
No. It's not because she's weak, it's because her arm is more like this, and when it hits her arm,
More energy.
more energy is transferring in. Okay? The speed of transfer. If the speed of transfer of energy in my arm was the same as the speed of transfer of this, what they call a snaky, instead of slinky. If they had the exact same speed, then all of the energy would go straight into my arm. Okay? Alright, now,
Break it off.
so Nia's arm goes with the same frequency as this big coil spring. Alright, Nia, let out some rope. Okay, now, the rope is in between. Let's see if we can do this. When the wave comes back, when the wave comes back, is it still on the same side or is it flipped over?
It's on the same side.
Notice it's on the same side this time. It's hard to see, but notice it's going to be on this side when it comes back.
Oh yeah.
You see? Why is that now?
Because it's less than.
Because the rope is less dense, less rigid than this. And so when the energy tries to transfer in, this is the side that gets flopped around, and it comes back on the same side. It doesn't flip itself over. Okay? So remember that. Thank you. When we get to reflections, you get two types of reflections. You can have a reflection that's upright or inverted, depending on what the wave hits. Okay? How the two mediums compare.
Space phone. From space.
All right.
Monkey.
Monkeys in space.
Now
Yeah.
Jews in space. Pigs in space.
Stop it.
That movie? Oh.
All right. If you're a Star Wars fan, anyone? Anyone?
Yeah.
Everyone raise your hand.
I will lightsaber with me. Luke, I am your father.
No.
Where's my child support? All right. Such a cheap trick in every ear. Whoa!
That's
All
why
right.
I made the noise?
Now you. All right. Now try it.
Aww.
Now take your end off.
Laser beam.
Yeah.
Okay, we need more. This is what's called a resonance, a resonator. It has more area to resonate the air, so it makes more sound. Now you can actually see the sound wave go down and back and watch the echo as you hear it, which
If
is
you
kind of
lengthen
cool.
it out, does it have a different pitch?
Yes. Well. Okay. So you can see it echoing back and forth, right? Okay. Okay, Rudy, hold this.
Yay!
But,
Success!
but you can't move.
I don't feel like I'm about to get changed.
You're moving.
Oh, this is really nice.
Okay, you ready? Everybody? So it's converting this type of motion back and forth into vibration at the ends,
I
right?
need one of those.
Okay, Google Space Phone. You can buy your own.
Just run down the hall really.
Time. That's so much fun. Make your legs tight.
Wait, can I do the Mickey Mouse way?
All right.
Come on, let's get that blue.
Okay, turn it that way.
Okay.
Thank you. Okay, let's talk about, all right, let's talk about another way to categorize waves. Okay, another way to categorize waves. Oh, by the way then, sound waves. Sound is always going to be,
Longitudinal.
okay, so sound is this. Okay, a transverse wave would be like guitar strings, or like you're beating a drum, the surface of a drum, okay, or like a wave in a slinky or something. It depends on how you strike the object sometimes as to what it's going to be. Like for instance, if I take this object and I took a hammer and I hit it on the end like this way, then what kind of wave did I make? Did I make transverse or longitudinal?
Transverse.
Because which way is the wave going to travel?
Go like that.
And which way is it going to vibrate? Up and down, right? Now, if I hit it this way, oops, I created a longitudinal wave this way. It should sound a little different. That one versus this one's got a higher pitch. Or this one has a lower pitch, right? They travel at different speeds. All right?
You have the rosin up there?
Yep.
Oh,
Okay. Look. All right. Waves can also be broken down into two other categories, whether they are mechanical or electromagnetic. Okay? Okay, mechanical waves require a physical medium. Okay? So, sound wave, does it require a physical medium?
Yeah.
Yes. If you're in space, can you hear sound? No. That's right. In space, no one can hear you scream. That's correct. Astronauts. How do astronauts hear each other? Radio waves. So a radio wave must be an electromagnetic
Not only
wave.
that, because they have air between them and the receivers.
Ah, so they have a receiver. They speak inside their little air bubble. They have sound that goes through the air to the receiver. The receiver picks it up and then transmits a radio wave to the other astronaut, which turns it into a sound wave inside the air bubble. Okay, what if their radios go out? How do astronauts communicate? They could use hand signals. They could write something down. Or they could take their fish bowl over their head and the fish bowl that the other person has. And they could touch them together and then yell at each other. Why would they need to yell?
Because it needs a lot of energy, because it's very dense.
Glass is really nice.
Because what happens is the sound goes through air, but when it hits the glass, what happens to some of the sound?
A lot of it
It reflects back, right? So they would touch their shields together, they would yell at each other, and they could hear each other quite easily. You can try that at home if you want. You can speak into well, actually some of you have done this before. You've made the little, the cups on the end of a string, and you've spoken into one cup and you can hear it out the other end of the cup. It does work.
You have to yell.
It does work.
Hearing it through the cut.
I know.
Yeah, I know.
Does it work better with metal?
Yes, it does. And why does it work better with
It's more
metal?
sturdy.
Because it's in this case, because I have a spring, it vibrates easier than the string does. It comes through easier. All right, and if you stretch it out, it's even more.
Whisper. Tell her a secret.
Whisper.
A secret.
No.
Hey, Melanie.
Yeah.
Hey, Melanie.
Space phone.
That's all right. Melanie's got a spare ear. She'll be fine. All right. So these require a medium. These do not require a medium. Can you give me any other waves that don't require a medium?
Light.
Light, radio. What else?
Infrared.
Micro, infrared. Oh my gosh, it's the electromagnetic spectrum. Radio,
Gamma.
micro, infrared,
Gamma.
visible,
Ultra.
Gamma.
ultraviolet,
Ray.
X,
Ray.
and gamma rays.
Ooh.
All of those are the only ones. Now, these also have a medium, but they have a self-propagating medium. They make their own medium. The way they do that is they have an oscillating electric and magnetic wave. Do you remember how we talked about how you can make an electricity flow by having a change in magnetic flux? Right? Okay, when you have a change in magnetic flux or a change in a magnetic field, you actually create an electric field. Well, you'll learn in Physics C that when you create an electric a changing electric field, you create a magnetic field. So what happens is the changing magnetic field creates an electric field, and the changing electric field recreates the magnetic field.
Oh my god.
And so it self-propagates itself through nothingness, through space, which is really cool. Okay, so these can travel through space, these cannot. This is why we can see the sun, but not hear the sun. Velocity equals change in displacement over change in time, correct? All right. How far does a wave travel in one time period?
Wavelength?
In one time period, how many waves are made?
One.
One,
Which is one wavelength.
which means it would go exactly one wavelength, right? So it would travel exactly one wavelength. But that's 1 over time period times wavelength, which is the same thing as frequency times wavelength. Now, everybody, this needs to be made very clear. The speed of the wave does not, I repeat, does not depend on the frequency and wavelength.
On the medium.
It depends on the medium. Very good. Very good for remembering that. It's not in the equation. There's actually equations for calculating the speed of a wave in different mediums, but there's a whole bunch of them for depending on what the medium is. So the deal is this is just a convenient way to calculate what it's going to be. But look, if I change the pitch of my voice to a new pitch, I've increased the frequency of my voice.
That's the natural pitch.
The velocity of my voice wave
Is the same.
is the same.
Because the lambda is
So therefore, lambda must go down. Okay, so what happens is the speed of the wave remains the same at all times in the same medium. So if you change the frequency, you're changing the wavelength, and they'll adjust each other to travel the exact same speed. Okay? All right. Now, by the way, the speed of sound in air. Velocity sound
Is this a constant we're gonna have to
in air is approximately about 340 meters per second. But approximately, it actually varies with temperature.
Isn't it 3.25?
Well, here's a pretty decent equation. It's 331.
362.7.
How does that convert to miles per hour?
Hang on.
156.
331.5 plus 0.6 t, but t equals temp
Pretty sure.
in degrees Celsius. So it varies with temperature. Okay, so be careful. If they say something about the speed of sound always being a certain speed, it's not true. It's if you change the medium, you change the speed, right? So if you change the temperature, it changes the medium a little bit. All right? Okay.
Oh, that's true. Are we gonna have to know that? Like, is there gonna be a question like plus 0.16?
No, but I just want you to know that the speed of sound in air they might give you 330, they might give you 340, they might actually give you the equation to figure it out. That's okay. You don't have to memorize it, just know it's around this speed.
Okay.
Hey, by the way, if the speed of sound then is about 333 meters per second, that's like a third of a kilometer, right? So that means if you see a lightning bolt, have you ever done this? You see a lightning bolt and you start counting.
Oh yeah.
1001, 1002, 1003, boom, you just heard it. It's exactly 1 kilometer away. Because the light travels how fast? These all travel 3e8.
I don't know kilometers though. This isn't.
Okay, now we don't want to know kilometers because we're in America. Okay? And since we're in America, we want miles. Okay, light travels nearly instantaneously, right? Okay, speed of sound in air is about 1/5 of a mile a second. So if you count to 5, it'll be a mile away. Now, if you're ever in a lightning storm and you see the lightning and hear it instantaneously,
You might want to get out of that.
yeah, lay down on the ground because you're in where the lightning's hitting, right?
On your rubber hat.
Yeah. Put on your rubber galoshes and lay down. Here's you, okay? And I'm paying you $1 to stand there and just do this. Boop,
But it's
boop, boop.
I do that.
Well, $1 per boop.
I do it. Hey.
All right, now, shh. You make your first boop. All right? And your sound wave travels out in a nice spherical shape from your head.
It's like a frog.
All right? And it's going outward. Starts here, goes out, goes out. Every second it goes out, what? About 340 meters every second. So here's what it looks like the first second. And then the second second, it's out here.
There's gravity.
And then it goes out further.
It's a really big
You went to the ground?
Here it's suspended.
He's on the edge of a cliff.
Okay, you all going to shut up and let me finish? All right, so it goes out every second the same amount. All right, and if you continue to make one every second, then you'll make a target pattern, right? And it'll look just like this. Right? However, what if you're moving? So here you are. You start here. You make your first sound. The sound wave goes out to right there. But by the time the sound wave has traveled there, you've moved. You make the sound and then you move. So you're right here. So do you see that you're near the front of the wave in the direction you're going, but it gets stretched out behind you, right?
Seemingly you're compressing the sound waves.
Yes. So what happens is you get something that looks like this. You're traveling this way with a velocity. You're compressing the waves in front of you and stretching the waves out behind you. The wavelength is changing. You have a smaller wavelength here and a much longer wavelength here. So the wavelength gets bigger behind you and the wavelength gets smaller in front of you. But wait, we said all waves travel at the same speed, the same medium. So this wave is traveling the same speed here as here. So what happens to my frequency up front? It goes up, and the frequency behind goes down. And the velocity is the same. Now you all know this. You've all heard it. All right. Anybody ever gone to?
Every time the ice cream truck passes by, and then it changes keys as it goes by.
Yes, that's exactly right. So the ice cream truck, as it goes by, it changes key. A police siren, when it goes by. It's not that bad, but watch it in a movie. It's easier to tell if you watch like a movie that shows a police car from Europe because it has a higher pitch note and it's easier to listen to. But have you ever gone to Texas Motor Speedway?
Yes.
What's the sound you hear? As they go by. High pitch to low pitch as it drops by, as it flies by, right? That's a classic Doppler shift sound, okay? This is called the Doppler shift, okay? But wait, what if you're going really fast? What if you're going the exact same speed as the wave itself? Sonic boom. Not yet, but close.
When you pass it.
So you're here, and here's the sound waves you're making. You're keeping right up with that front wave. So your velocity here equals the velocity of sound. Your velocity here is greater than 0 but less than the velocity of sound. Your velocity here is 0. Okay, so what happens when you go faster than the speed of sound?
There you have it.
There you are. And here's your sound waves.
Ooh.
So, there are two ways to sneak up on someone.
You got it really, really quiet.
Really quiet,
Or you
or you travel at them faster than the speed of sound, and they cannot hear you coming. Right? Yeah, so like you're running at somebody faster than the speed of sound, and you're yelling at them, "Get out of the way! Get out of the way!" They don't hear anything,
You gotta slow down.
and then you hit them, and then they hear, "Get out of the way!"
They're gonna think they're hallucinating.
That's right.
Oh, no.
In the old Western movies, you know, the guy got shot, and he's like, "Oh, I heard the bullet coming." No, you didn't. Because the bullet travels faster than the speed of sound. You got hit, and then you heard it. All right?
Wait, so if you're not looking directly at a bullet, you don't know if it's coming at you before it hits you?
Unless it's really.
Your eyes can't pick it up because they can't see something moving that fast.
But you can see nothing around.
You can see the flash.
No, but like if I'm turned this way and you shoot me,
the other way,
by the time I hear it, I'm gonna be
back.
dead, right?
Yeah.
Like so.
You'll be dying. You'll be dying.
All right. This, by the way, so your velocity is greater than the velocity of sound. This is called a Mach cone. That's called a Mach cone. This is the zone of noise, and out front is called the zone of silence.
So that's what they call Mach 1, Mach 2.
Yes, so this is Mach number 1, or Mach equals 1. This is Mach greater than 1. This is Mach less than 1. And this is Mach 0. So Mach number is just your speed divided by the speed of sound. That's it. So if something's going Mach 1.2, it's going 20% faster than the speed of sound. If you're going Mach 2, you're going twice the speed of sound. All right? Space shuttle, when it re-enters, it's going like Mach 25. Okay? Really fast. 25 times the speed of sound.
And when it leaves, it goes fast too.
Yeah, not quite that fast though.
Because it's going against gravity.
Yeah. All right. So there you go. This is called Doppler shift. Now there's an equation for this. All right? What? Hang on. Back up. You can get this Doppler shift two ways. The sound source can be crunching or stretching out the wave. Or the sound receiver can be stretching out or crunching the wave. Like for instance, if you're standing there talking to me and I run at you,
It gets high pitch.
it gets high pitch.
I get scared.
Now if you're talking and I run away from you,
Because it's all one thing.
because I don't want to hear you, then it goes low pitch. This happens in all waves, everybody, no matter what kind of wave. So wait a minute. What if you're sitting there and you're wearing a red shirt and I run at you really fast?
It looks more.
The waves get crunched, the wavelength goes down,
So you see it.
so I would see ROYGBIV, Roy G. Biv, red shirt. This is the longest wavelength, this is the shortest wavelength. So if I would run at you, your shirt would go orange and yellow and green and blue and violet if I run at you really fast. And if I would run away from you, your shirt would...
You cease to see.
Become invisible.
Would it become invisible, or would I just see... What would I see? What is that when you don't get any light from it? What's it called?
Black.
Black. Your shirt would turn black because I can't see that frequency. It's kind of cool. That's called red shift. If the object is going away, if they're going away from each other, it's red shift. Blue shift if you're going closer. This is how they tell how fast stars are going and why they say the universe is expanding. Because they look out at all the stars and all the light from them are red shifted. So that means the stars are all moving away from us. So the universe is expanding.
Or maybe
All right.
we just scared them.
Yeah, we scared them. You want to play. All right, so red shift or blue shift, they call it. Okay, this is why you got your last speeding ticket. Because the police officer shot a laser at you, and the laser hit your car and bounced back. And when it bounced back, it's a different frequency. If you're going towards the police officer, it's been scrunched. If you're going away from the police officer, it's been stretched out. And then the machine reads the difference in frequency, calculates the speed. How does it calculate the speed, you ask? Well, by this little equation. Oh, okay. Good question. And by the way, all of you have seen a sonic boom, except you haven't seen one in air. You've all seen one in water. You've all seen what's called a shock wave. This is called a shock wave right here. And what it is that the air cannot move out of the way. It doesn't know the sound is coming towards it. So all the air builds up in this cone ridge. It's a high pressure ridge. And that creates a booming sound when it goes past you. Okay? It's like if you're here on the ground, the plane passes you by, boom, you don't hear it, and then all of a sudden the boom passes you, and then you hear the sound.
I like how planes go by and car alarms start going off.
Yes. Some of you have experienced this. You've heard a plane, like maybe a jet plane, like a military plane go overhead, and you look to where you hear the sound, and the plane's not there, and you're like, where is it? Well, it's already gone past. Right? Because it takes time for the sound to get to you. Except in a Mach cone, it's like a big boom when it goes past. When the sound goes past. Okay, you've all seen this. You've all seen this. No, a boat in water.
Oh yeah.
Oh.
It's moving
Right?
forward,
You've all seen a Mach cone for a boat in water. The boat is traveling faster than the speed of the waves in water. So it creates a wake. They call it a wake in water. It's a Mach cone. Okay? So you're traveling faster than the speed of the water and waves in water. Water and waves. Now, any of you boaters? Anyone? Okay. When you're in a boat and you're going real slow, the boat sinks in the water, and then when you hit the gas and you take off, the boat will go bump, 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 and all of a sudden it will plane up and kind of get up on top of the water, and you go real smooth. That's when you go faster than the speed of the wave in water, and the water cannot get out of the way, and the water doesn't build up in front of you. You just glide across the top of it. Anyway, so here's your equation for Doppler.
What is that word?
Observe, sorry. Okay, everybody, there are several ways to write this equation. This is just one way to write it. Okay? You've got frequency of the source. That's the sound making thing. And then you got the frequency of the observer. That's the sound receiver. Okay, the sound that is heard is the frequency of the observer. That is observed. You might want to put, I should put observed. Sorry, not observer. That's the observed sound. What you perceive as the sound. Okay? Okay, VO. What's VO then? Velocity of the observer. And Vs is the velocity of the sound source. Okay? All right.
What's V? V is just the speed of sound.
Okay, so what's V?
So it's like Mach.
Yes, so it's kind of like that. Now look, if I want the observed frequency to be higher, then that means the top has to be a bigger number, or the bottom down here has to be a smaller number, right? All right, so the deal is that the... Oh, I got to talk sign convention too. One last thing. Here we go. We'll do it this way. Here's a car. Let's say the car is traveling this way, and here's a person that's not too happy because the car is coming at them.
And they're running that way.
And they're running this way.
Just run to the side.
This is the velocity of the source. No. This is the velocity of the source. This is the velocity of the observer because the car is honking at the person. Okay? Now here's the sign convention. The velocities are considered positive if they're approaching the other. Okay? So, the velocity of the car, is this a positive velocity or negative velocity?
Positive.
It's a positive velocity because it's approaching the other. The velocity of the observer, is it a positive velocity or negative?
Negative.
Negative velocity because it's trying to increase the distance between the two. Alright?
And then you could also have the other way around, switch VS and VO and see how the car driver hears the person running.
You could do that as well. Now I want you to notice something. What if VO and VS are the same?
That means that
Then he's safe as long as he can maintain that speed.
Okay, the person would be safe for one, but what would they hear? Would they hear the actual sound of the horn, a higher pitch or a lower pitch?
The same exact.
Let's look. If, let's say it's 10. Let's say this is 10 and this is 10.
It's a higher.
Then look what I get. I get 10 right here divided by about 340, right? But this is a negative 10 because it's the observer, right? Okay, right here, I get a 10. It's positive because it's the source, over 340. So look what I get. 1 plus negative 10 over 40, and 1 minus 10 over 340. So it should turn out to be 1, right? And so you get no change in frequency. Okay, here's the deal. In order to have a change in frequency, the distance in between has to decrease to get a higher pitch, or the distance has to be increasing with time to get a lower pitch. All right? Let me see if I can show you that.
You know, we could really use some of that.
You could use some of this. You're running out of this stuff?
The distance increases to higher or lower pitch.
If the distance increases, then the waves are getting stretched out. So it's a lower pitch. All right.
Yes, more.
So I just moved that.
Now listen. Listen. You hear the wobble in the sound? High, low, high, low. As it comes towards you, it's higher pitch. As it goes away from you, it's a lower pitch. You hear it?
Put that inside space.
Do it.
Do it.
Stretch it out.
All right. Now, so that is Doppler effect. Okay, make sure you get your sign conventions right. Most of the time on the test, they don't have an actual numerical problem with Doppler effect. You just got to realize when the distance is decreasing between them, the pitch goes up. Frequency goes up. When the distance is increasing, the pitch goes down. Frequency goes down. All right? Okay, let's talk about two other important things of waves. Okay, waves. Since waves are a disturbance, and the waves take up space as they oscillate, okay? If they go around a corner or a boundary, so like there's a boundary or something like this that they go by, what happens is the waves will change path because they'll be interfered with by the boundary. So if you had a whole bunch of waves coming up this way, so like water waves, if you're in a helicopter looking at water waves approaching like a boundary, the water waves are traveling this way. So here's all the waves lined up coming towards the shore. Shore's down here, but they got boats back here, so they got a wall to block the waves, all right? You would expect the waves to go by like this, okay? And over here they do, but right here what happens is they will be interfered with by the boundary and they'll bend around the corner. So they'll come in like this and turn. Right? This is called diffraction. Diffraction. All right, so if you have an opening like this, and the light wave comes up like this, it'll bend around the corner and create a rainbow. Not really a rainbow, but it'll bend into what looks like a rainbow shape of wave fronts. So the wave is coming this way, it goes through and bends around. Okay? We will talk about that a little bit more later because there's a lot more to it, but you can actually see this. Well, you can hear it in your house. In your house.
Yeah.
Now, think about it for a second. What if the wave was really tiny? So I have this opening, and I have tiny waves going through here. Do you think they'll be interfered with much by the boundary? Small. They're like little bitty waves. Small wavelength. Okay, these will shoot mostly straight through. But the longer the wavelength, in fact, if this opening is about the same size as the wavelength, or smaller, if this is smaller than the wavelength, then you'll get a lot of this diffraction. The bigger the opening is compared to the waves, the less it'll interfere with the wave and the less it'll bend around the corner. Okay? Now, you've all experienced this sometime in your life. Somebody in the back room of the house or apartment is playing the stereo, playing music,
That's usually me.
and someone's in the front of the house. What type of music do you hear the most? What part of the music range do you hear the most?
Bass.
You hear the bass. The bass travels all the way through the house because it's bending around corners, because the bass waves are really long wavelength, because they're low frequency, therefore very long wavelength, right? The treble is a much smaller wave, so therefore it doesn't bend around the corners as much. If you have a subwoofer is just a big old speaker that you sit anywhere in the room. And it fills up the entire room with this bass sound because it bends around the couch, it bends around the people, okay? And fills up the entire room. You can't do that with a high-pitched speaker. Those little cube speakers, they put those up high on the wall and point them into the room, right? Because the little cubes have to point the sound waves where you want them to go because they're not going to bend around the corners as well, right? Okay. All right, that's called diffraction. You want to see diffraction? Okay, everybody. Yes. Take your fingers go like this.
No, I never liked this.
You've done this already? Look up at the light. Hold your fingers really close together until they almost feel like they're touching. And when you do, you'll start to see your fingers look like they bleed together.
Yeah.
And sometimes you'll even see the lines in between your fingers. So it'll look like this. One finger up here, the other finger down here, and you'll see a whole bunch of lines
Whoa, I just can't see that.
in between your fingers. You see it?
I might see one or two.
You kind of have to hold it real close to your face, pretty close like this, like around your nose or closer.
See.
Really now.
You see them bleed together? Those are a bunch of lines. That's because the light is bending around the corner.
I do.
And we'll talk about why you get those lines in a couple days.
Diffraction.
Yeah, it's called diffraction patterns. Say you have a wave like this, traveling at a wave that looks like this.
Brings up something like an error at the bottom of the screen. It's me.
Hey. Wave like this, traveling at a wave like this. When they meet, they will combine, and their motion in the medium will be the addition of the two. So when they meet, it'll look like this. Well, it could look like this. Oops.
Assuming halfway or what?
Actually, this will be even higher. This one and this one adding up when this is right here, right? And then it will move through the other one, and so it'll look like this.
Halfway.
Halfway through, as this one moves this way and this one moves this way. All right? Okay. On your e-homework, they give you a really crazy one. They give you a crazy wave pattern.
Well, it looks like it's like.
All right?
Yeah.
And they have the waves traveling at each other.
Because they're evil waves.
And they are evil waves. You'll have a wave like that, and then you'll have another one like this.
Just add everything.
I hate that.
Okay, I'll give you a hint, everybody. They'll tell you how fast each wave's going. I think it's the same speed. All right?
And then you give you the time.
Hey, I'll give you a hint. Why don't you do this? If this one's traveling to the right at V and this one's traveling to the left at V, that would be the same as if this one's traveling to V and this one's stationary, right? Wouldn't that be the same thing? Wouldn't they approach each other at the exact same speed? So hold one still, and then take this one and figure out where it's going to be overlapping the other one. So like if this is, up +1 and that's +2 above, and that's +1, that's +1.5, and that's +2.
1.5.
If they overlap, and say this part overlaps with this part, then that would be up +4, right?
Okay.
Yeah. Oh,
That make
totally.
sense?
Yeah.
Yeah.
Okay.
And then what about
And if this is -2, and that's adding on to this +1 right there, then what would you get? You get a -1 at that location, right? Okay.
Alright.
Okay, we're out of time.
Guys, we have all the time in the world.
We will do interference, and we will start doing sound in pipes and strings and all that stuff next time.